There are two inference procedures that we use in linear regression. They both apply to the true slope, which is an unknown parameter. We're going to estimate it using data, and we're going to answer questions or test claims about it using tests of significance. Now, the first procedure we'll do is the confidence interval for beta. The purpose is to estimate the true slope beta. The conditions are in the preceding video and the introduction to inference for regression. The formula is b plus or minus t star times SE of b. We have a statistic plus or minus a critical value times the standard error. This is the standard error of b, our slope coefficient from our data. And this confidence interval uses n minus 2 degrees of freedom. So this t star right here you would get from the column in your t-table that has the level of confidence that you want, and it'll be in the row that has n minus 2 degrees of freedom. That's where you get that. The standard error of b is calculated from this. It's the standard error about the line s, which we looked at in the preceding video, divided by this big square root, the square root of the sum of the deviations in x from their mean squared. And that's something you're typically not going to have to calculate yourself. Probably never. Most of the time when you're working with this, you'll be working with computer output, and you won't have to calculate this yourself. That will be provided as part of the computer output. If you do this procedure on your calculator, it only works on TI-84s. You have to do stat test G lin reg T interval. The other procedure we're going to look at is the linear regression t-test. In this procedure, the purpose is to test the null hypothesis that beta is equal to beta naught. Beta is the true slope. Beta naught is some hypothesized value of that. Typically, beta naught is equal to 0, but not always. And what you most often want to see is whether or not there is a linear association between your response and explanatory variables. And if beta naught is equal to 0, if beta equals 0, then there would not be a linear association. There would also not be a linear correlation between your response and explanatory variables. But even though beta naught is typically 0, it's not always 0. And there was a question on the exam a few years ago where beta naught was equal to 1, and it threw a lot of people off. So beware of that. The conditions we checked in the preceding video. The formula is another standardized test statistic, b minus beta naught divided by the standard error of b. Okay, b is your calculated slope from your regression line. Beta naught is from your null hypothesis. That's a hypothesized mean value. And then the standard error of b divided. So it's a standardized test statistic. Statistic minus hypothesized mean divided by standard error of the statistic. On your calculator, you can find this as stat test F, lin reg T test. And this is available on both TI-83s and TI-84s. Let's look at an example of how this works. Here's a table of data. We've got the number of jet skis in use in this column and the number of jet ski related fatalities in this column for the years from 1987 to 1996. And we want to construct a 95% confidence interval for the true slope of the linear relationship between fatalities and jet skis in use. And we want to test the null hypothesis of no linear association versus the alternative of a positive linear association between jet skis and fatalities. In this case, fatalities is your response variable. That's your y. That's what you're trying to explain. Jet skis is your explanatory variable. That's the variable you're using to predict or explain the behavior of your y variable, fatalities. Now, if you're working from these data, the first thing you'd want to do is put the data into your calculator. So you turn your calculator on and go into Stat Edit and put the data in there. Okay? Next step is to make a scatter plot of the data and see if it's suitable for linear regression. So what you do is you go into Stat Plot and you select any plot on here, but make sure it's the only one that's on. On the type line, you want to select the first one, and then you want to use the list where your jet skis and fatalities are stored. In this case, they're in L1 and L2, and then you select your symbol. And then once you have that, you can go zoom 9, and your calculator will make the scatter plot. Now this scatter plot is fairly linear, so it looks appropriate for what we're about to do. The next thing you want to do, though, is check the residuals But you can't check the residuals until you've seen, you can't find them until you've done the linear regression itself. So what we're going to do is we're going to go stat calc 8, and then we're going to do a linear regression using the x's from list 1 and the y's from list 2, and then we're going to store those in y1. So we go to vars, go over to yvars function and y1, and then when we run the regression line will be stored in the y equals screen. And you can see our y-intercept is about 7.9959, our slope is about 0.0662, our r-squared is about 8679. That means about 86.79% of the observed variation in jet ski fatalities is explained by the least squares regression of fatalities on jet skis in use. And then r is 0.9316. That indicates a strong positive linear association between fatalities and jet skis in use. Now we're going to look at our residual plot. The residuals from this regression are stored in the calculator, and the way to find them is to go to second stat, and they're down on this list right here. So you go down there and you can find them, and stored in RESID, that list right there. Okay, we'll come back to that in a second. Before we do the residual plot, we have to respecify our scatter plot. We are going to change the Y list from L2 to RESID. So we're going to go to stat lists, or second stat rather, and we're going to pull that RESID list out, and we're going to put that in here as the Y list, and then we can use the same symbol that we used before. Now I've stored my regression line in the Y equals screen, and it's in there, and I don't want to show it on the residual plot, so I'm going to toggle that off for the time being, and then I'm going to go zoom 9 and make my residual plot. Now you can see it doesn't show much of a pattern. There's a fairly regular or uniform amount of scatter across the plot as you go from left to right. So there may be a little bit more scatter on the right than on the left. There doesn't seem to be any kind of like wave-like pattern or anything else like that in the data. So it looks like the observations are independent, and it looks like there's fairly uniform scatter. So the first three conditions are pretty well met. We have a scatter plot that's fairly straight. We have a residual plot that shows no strong pattern. We have observations apparently independent because the residual plot shows no kind of a pattern, and fairly uniform spread in the residuals all the way across. The fourth thing we have to check is for the residuals to be normally distributed. So this is what we'll do. We'll go to stat plot again, and we'll change our first plot to a normal probability plot. So on the type line, you're going to go all the way to the right and select that one, and then it'll ask you, where are your data? Well, what we're going to use for this data list is the residuals. So we're going to toggle down to there, and we're going to go to second stat again, and from the names list, we're going to pull out the residual list. There it is. And then we're going to make the normal probability plot of that. And we can use the same mark that we used before. And if we go zoom 9 now, we get that normal probability plot. And it looks very strongly linear, and that's a good thing. If the residuals make a linear normal probability plot, then you can believe that the residuals are approximately normally distributed, and that meets the condition. Now, we're about to do the test. So we've checked the conditions. The true relationship appears to be linear. The observations appear to be independent. The spread about the true line appears to be uniform, and the spread, the y values in terms of how they're distributed around the true line appear to be normally distributed. So we're going to go ahead and do these procedures. Now we'll clear this graph, and we'll go to stat tests, and then we'll pick out the linear regression t-interval first. All it asks you for is where are your x's and y's, and they're in list 1 and list 2. So make frequency be 1. Typically, if you're working with all the data in those lists, you don't have to do anything with that. Let's do 90% confidence, and we'll we're doing 95% confidence, so 0.95, and then we'll our regression equation is stored in y1, and we'll calculate, and here comes our interval, 0.04515 to 0.08728. It gives us our B, it gives us our S, it gives us our A again. So we've got the three statistics that we use in this procedure, and we've got our degrees of freedom down here. There's a little bit more that gives us the R squared and the R again. So pretty complete little treatment of the regression results there. And then if you want to do the linear regression t-test, go to stat tests, and then down here to linreg t-test, stat test F, and then again our data are in list 1 and list 2. We'll select this alternative over here because the alternative we're using is that beta is positive. And again, the same regression equation we'll calculate, and here is your t-statistic, 7.2493 approximately. P-value is very small. That's 4.4 times 10 to the minus 5. It's very close to 0. Again, you got your degrees of freedom, your A, B, S, R squared, and R all given as in the results of this procedure. So based on that, we could reject the null hypothesis of no linear association, and we find pretty strong evidence that there is a strong positive linear association between fatalities and jet skis in use. Next, we'll go to we'll look at this test done from computer output, which is a lot more convenient. Now, when you're working with computer output, you're going to get typically something like this, where the computer says dependent variable is this or that. That's your Y variable, in this case fatalities. And down here in this table, it's going to give you predictor, constant, or jet skis. Right here, this means the y-intercept, and this means the x variable right there. And then it gives you those coefficients. Here's the coefficient for the y-intercept, 7.9959. So that right there is A. Okay, that's the y-intercept of your regression line. This value right here is B. That's the slope of your regression line. Down here at the bottom, they give you S, the standard error about the line. That's the third statistic that we use in regression inference. And over here, this in the standard deviation column, we have 0.0091. That is the standard error of B. And then it gives us a t ratio and a p-value. Okay, this is the t. This is what the t statistic would be if beta naught is equal to 0. And down here we've got R squared and R again. And from these pieces of information, we can do our inference procedure. Okay, the least squares regression line from these numbers here is predicted fatalities equals 7.9959 plus 0.0662 times jet skis. The 90% confidence interval for beta would look like B plus or minus T star times SE of B. Now we go to the T table to get this. We have 8 degrees of freedom, and 90% confidence gives us 1.860 from the table. Then we plug in the other things from the computer output, and we simplify it down. We get 0.0492 to 0.0832, which is not quite the same as what the calculator gave us, because we have some rounding error in here, and that's primarily, why our answers don't perfectly agree, but they're pretty close. And then secondly, if we want to do the t-test, the null hypothesis is that beta is equal to 0. The alternative is beta is greater than 0, and our t-statistic is B minus beta naught over SE of B. We get all this stuff from our computer output, and this comes from the null hypothesis. That simplifies down to a t-statistic of 7.2747, and our p-value using t-CDF on the calculator gives us approximately 4.3 times 10 to the minus 5th. When we did the test from the data on the calculator, we got 4.4 times 10 to the minus 5th. Either way, you're going to reject the null hypothesis. And that's how it's done. It's actually quite simple. It's a lot easier